Good evening. Tonight, we will have a presentation on improving the VR experience by understanding the human visual system. This will be presented by Brooke Krajancich from Stanford University. This will be the first of two joint meetings co-hosted by Silicon Valley SIGGRAPH along with SFBayACM. I would like to thank SFBayACM for co-sponsoring this event. I am Alex Junkarek, chair of Silicon Valley SIGGRAPH chapter. Before we get to tonight's presentation, let me first introduce you to our organization. So SFBayACM and Silicon Valley ACM SIGGRAPH are chapters of the international organization ACM and ACM Special Interest Group on Computer Graphics ACM SIGGRAPH, respectively. Our parent organization supports their members by providing opportunities for continued education, networking, and job hunting. One of the ways ACM SIGGRAPH supports its members is through two SIGGRAPH conferences, one in North America and a second in Asia. I want to mention that registration for SIGGRAPH is now open. SIGGRAPH is a great way to immerse yourself in computer graphics for 1 week. It's always been one of my favorite events each year, and this year will be special since it's the 50th SIGGRAPH. Personally, I'm always sad when the SIGGRAPH conference ends. However, for me as an officer in Silicon Valley SIGGRAPH, the end of the SIGGRAPH conference is just the beginning, because at Silicon Valley SIGGRAPH, we try to keep the excitement of the conference going all year long with our monthly meetings. Okay, both Silicon Valley SIGGRAPH and SFBayACM typically meet in various Silicon Valley companies about once a month. Our meetings are great for networking and learning the latest technologies. We also have job announcements from time to time. Since COVID hit, we have been online. However, we hope to get back to in-person meetings eventually. So at this point, I'd like to invite Bill Bruns to say something about SFBayACM. Bill?
Yes, thank you. As Alex said, this is a jointly sponsored meeting, although SIGGRAPH is doing most of the setup and managing of the meeting for this meeting. And we have another one coming up next month as well, which is a joint meeting on VR, AR from another perspective. And Silicon Valley SIGGRAPH, as he said, is part of ACM, and the SFBayACM is the organization that I'm part of. And we have a meetup page and a YouTube channel that you can look at to see our many saved meetings and videos of meetings. We've been around since 1954, and we do try to have 2 meetings a month, one on general computing, anything about computing, and the other about anything related to data science, big data, that type of thing. So, and we, I think both organizations are totally volunteer led, and we are always happy to have volunteers to participate. Please take a look at our website, sfbayacm.org, and our YouTube and meetup channels. Thank you.
Okay, thank you, Bill. So as Bill said, next month we will have another VR meeting, which will be hosted by ACM. And if you want to find out more about ACM, please come to that meeting also. But for tonight, I'm going to introduce you to some of the volunteers which helped put this meeting together from Silicon Valley SIGGRAPH. So first off, I am Alex Junkarek. I'm the chair of the chapter. Brent Simon is vice chair. Carl Anderson is treasurer. And Ken Turkowski is a member at large. And finally, the next volunteer could be you, because we are also always looking for new volunteers. And being a volunteer isn't, of course, is not a paid position. However, there are advantages to being a volunteer. It's a great way to network since you're always putting meetings together for speakers, so you have a chance to interact with the speakers. You can also help organize meetings around your interests. Finally, it's always a fun group of people to work with, so we always have a lot of fun working together as volunteers. People ask, what are the time requirements? There is no particular time requirements, so each volunteer just gives whatever time they have, and that defines what meeting that we can have next. If this sounds good to you, you can consider contacting us and volunteering. So we also have to find us. You can find us through our website. We have a Meetup page on Meetup, or you can email us through this email. A lot of our meetings are also recorded, and you can view these old meetings on YouTube. So for those of you who are watching this on YouTube now, these links will be in the description. However, if you want to find this information later, you can go to Google and type in Silicon Valley SIGGRAPH. Let me tell you about our upcoming meeting. I think which was already mentioned that we will also have another. Okay, so this will be the second meeting co-hosted with SFBayACM, and it will take on place on May 17th. And this meeting will be on human-centered design for VR training. And the speaker will be Dr. Jason Gerald, CEO of NextGen Interactions and lead VR advisor at XMod. So this presentation is for VR creators and stakeholders that are seeking insight on how to define, design, and evaluate impactful training. So please visit our Meetup for more details. And now, I would like to introduce our speaker for tonight. Tonight, Brooke Krajancich will be speaking on improving VR AR experiences by understanding the human visual system. Brooke Krajancich is a final year PhD candidate in the Electrical and Engineering Department at Stanford University, advised by Professor Gordon Wettstein. Her research focuses on developing computational techniques that leverage the code design of optical elements, image processing algorithms, and implement knowledge of the human visual system for improving current generation virtual and augmented reality displays. She's actively looking for a full-time position starting this June. For more information on Brooke, please visit our website. And now, please welcome Brooke Krajancich, our speaker for tonight.
Hi, everyone. Welcome to my talk. Thanks for coming. As Alicia kindly introduced, my name is Brooke. I am a final year PhD student. I'm actually a couple of weeks out for defending, so I'd love to keep this talk pretty casual. Like, please feel free. I'll try and monitor the Q&A and the comments, the chat section as I'm going, but please feel free to post questions and interrupt. Like, I'd love to have a discussion wherever possible. I also welcome feedback on the presentation, as I'll be using a lot of it for a defense in a couple of weeks. So always love outside perspectives on what can be made better. I will make one correction to the introduction. I am no longer looking for a job. Finally, I did get one. So excited about that. But with that, let's launch right into it. Okay, so virtual and augmented reality, or VR and AR, are next generation display systems that unlock new user experiences by offering unprecedented levels of immersion. I'm sure you're all very familiar. So with the ability to feed us information or place us in environments that would be otherwise infeasible or dangerous, these systems have already enabled innovative solutions in many fields. For example, in some of my favorites, education and business, VR, so at the top here, VR has been used to promote diversity, equity and inclusion with immersive empathy training, while in medicine, in the center here, AR has helped give surgeons like X-ray vision, if you will, by allowing them to visualize preoperative scans actually superimposed on their patients. Or you might have watched Chris Hemsworth pretty recently in the National Geographic show Limitless. They used VR training to sort of train his stress levels while strutting across a crane dangling 900 feet above in a skyscraper. So he practiced on this rig set up in a warehouse before going and actually doing it for real. So you can imagine for many of these applications, it is desirable, if not critical, that these displays create visual experiences that feel real. So that is, they are what we call perceptually realistic. So to quantify what is really a feeling, the research community has actually adopted the visual Turing test as kind of a North Star. So similar to the Turing test devised by Alan Turing in 1950 to evaluate whether a computer can pass for a human, the visual Turing test evaluates whether what's displayed by a VR or AR display can be distinguished from the real world. It's a subjective test, and it's one that no VR or AR technology can pass today. So while they've both come a long way, neither is at the level where anyone would truly wonder whether what they are looking at is real or virtual. Now, the most commonly talked about issue is just purely getting enough pixels on a display. To be able to pass this visual Turing test, we need to form an image on the retina such that we cannot tell that photons are emitted from discrete pixel locations or from a display that does not cover like the full 360-degree sphere. So we need a display that covers, well, at least the field of view of the visual system, which is huge, a whopping 220 by 135 degrees, thereabouts, with pixels smaller than our spatial resolving capacity. So that's about 40 cycles per degree, which equates to about 80 pixels per degree. So you can do some quick math there, and straight away you're getting about 13,000 pixels just in the horizontal direction, which is far more than any consumer display that we have available right now. So short of this, we're forced to make a trade-off, and you can often hear of this. It's often referred to as the resolution field of view trade-off. So we've got a set number of pixels we can work with, the most that we can put on a display panel, and we have to make a trade-off between how much field of view and how much resolution we're going to get. And this results in artifacts such as this screen door effect, which you can view if you go up to your TV screen with a magnifying glass. That's the effect that you're seeing. Or just a really small content area, as you can see by the HoloLens field of view here, which essentially detracts from this perceptual realism, this ability to pass this Turing test. But even if current display technology could meet these specifications, drive and operate that many pixels, GPU performance budgets are far from that required to render such an enormous number of pixels, not to mention compressing and transmitting the 17 billion pixels per second that would approximately equate to. Now, to put that into perspective, we'd need around 8 HDMI 2.1 cables to move 400 gigabits per second. It's whopping. However, many of these pixels are squandered due to the fact that we have varying perceptual capabilities across our visual field. For one, only a small central region of our retina, about 1.5 degrees in diameter, called the fovea, is actually responsible for that spatial resolving capacity that I talked about. Outside the fovea, this falls off pretty rapidly. In fact, by about 20 degrees of eccentricity, it's already dropped by about 90%. So if we built a display that covered our entire visual field, well, over 95% of the pixels would be outside of that region. So it seems like a bit of a waste to have to put that many pixels there. So with recent developments in wearable eye tracking devices, it's no surprise that perceptually aware computer graphics approaches have drawn extensive attention from various applications. So in particular, I'll be talking about Gaze-Contingent rendering and display, which has emerged as a promising solution to the bandwidth challenges that I talked about around VR and AR, attempting to balance the amount of information displayed against the visual information processing capacity of the observer in that particular moment through real-time gaze prediction, position prediction. So perhaps the most well-known of these approaches is Foveated Rendering, where rendering quality is progressively decreased towards the periphery to reduce the number of vertices or fragments, various approaches. A GPU has to sample, ray trace, shade, or transmit to the display. But knowledge of gaze and eye position can also be used to do other things, like render dynamic gaze effects. So these are visual effects that occur depending on where you are looking within a scene. So for example, focus cues, like that depth of field blur that you kind of get when you're focusing on something close to your face versus further away. And pupil swim, for example, which is an effect that occurs because of the distortion of the lenses in a VR or AR headset as you move your eyes. So things that happen because your eyes are constantly moving. So today I'm going to talk about two of my recent projects that aim to create more perceptually realistic VR and AR experiences by understanding the visual system, and in particular using this sort of gaze-contingent display paradigm. Both of these projects were done in collaboration with my advisor, Gordon Wetstein, and I also want to recognize Professor Peter Kellenhofer, who is now at TU Delft, who worked on these projects with me. Okay, but first, let's talk about foveated rendering. How does it work today? Well, foveated rendering encapsulates this suite of techniques that build on the insight that our acuity or spatial resolution varies across the retina. Now, there's lots of techniques that have demonstrated different ways to perform this degradation, transition between regions, even approximate this sort of fall off as you go out, of visual acuity as you go out towards the periphery. However, common wisdom suggests that sensitivity to temporal modulation also varies across the retina. In fact, it is anti-foveated in that it peaks in the mid-periphery. So you might have seen this. Actually, this was inspired by, if you go out, sometimes you can see like a street lamp like flickering in your periphery, and you're like, oh, that light's annoying. But then you go to look at it and it looks stationary. It's because we have a higher sensitivity to that flicker actually in our periphery, probably to escape predators or some evolutionary reason. I'd believe that. But yet we have not used this, have not seen this used to save bandwidth. And this is in part due to a lack of a well-known model for temporal resolution, like we have the visual acuity curve. This has been well studied. But the visual system is also far more complex with other limitations that could aid in saving bandwidth. For example, our spatial and temporal sensitivities are not independent of each other, nor are they independent of luminance. A high spatial frequency may appear static, but reduce it a little and suddenly it starts to flicker without any change to its temporal frequency. And then you drop the brightness and it appears static again. And of course, all of this interplay depends on where the stimulus falls on the retina. And yet, while we know trends, we don't currently have a unified perceptual model for these eccentricity-dependent spatial temporal aspects of human vision, preventing us from achieving the full potential of foveated graphics for saving bandwidth. Which is exactly what we addressed in our SIGGRAPH 2021 paper. But before I jump into talking about how we measured spatial temporal sensitivity across the retina, I want to quickly introduce, or maybe for some of you, probably some of you, review a few concepts from vision science that will perhaps motivate why this hasn't been done until now. So the basis of vision comes from variations in light intensity over space and time. Now, as we know, sinusoids provide a systematic way to describe the sensitivity to these variations, since we can constitute any waveform with a sum of sinusoids with different amplitudes and frequencies, simple Fourier. Contrast is the ratio of the variance in the luminance to the mean luminance. It's commonly used to characterize our sensitivity to these patterns. More specifically, we can reduce this contrast until the user can only just identify the orientation of the pattern. So in this case, it's 45 degrees. This is referred to as the contrast threshold, and then 1 over that characterizes our sensitivity to this pattern, since a small detectable contrast means a higher sensitivity. So if we repeat this for different temporal modulation frequencies, we can plot out a curve called the temporal contrast sensitivity function, or TCSF. And similarly, we can repeat this for different spatial frequencies and plot out the spatial contrast sensitivity function, or SCSF. But if every signal has both a spatial and temporal frequency, so if you squint hard enough, you might be able to see that we can combine these to plot the spatial temporal contrast sensitivity function, or STCSF. So this is very interesting to us, but to be of use in foveated rendering, we need a plot like this for every point on the retina. Now, while conceptually simple, such a model is hugely impractical to sample. To converge on a threshold for 3 different axes, so spatial frequency, temporal frequency, and eccentricity for all combinations and luminance would be highly susceptible to user fatigue, and it would take like several days per user. Furthermore, existing data sets sample along 2 of these axes at best, and often under different conditions, and display luminances and modulation patterns, or with and without one eye covered. So it's difficult to combine existing models or fit a new model to existing data due to the sparsity of data across the higher dimensional space. I'll put a bit of an asterisk here and say that since I did this project, another author published a paper that did this, and that has its pros and cons, and we can discuss that later. That was last year at SIGGRAPH, but just go with me for now. But while STCSF is a rigorous model of the visual system, in foveated rendering, actually we care most about its footprint. Since the vertical axis here is sensitivity, anything above the floor means that we have some sensitivity to the signal. So this boundary here encloses the gamut of all visible signals. So then the furthest points along the X and Y axis then define the highest frequencies that we can see, which can be thought of like our spatial and temporal like resolutions. As such, we set up to measure a conservative bound on this gamut by setting the sinusoidal patterns to maximum contrast, and then removing the sensitivity axis altogether, which significantly reduces the space that we need to sample. So essentially we sample like a binary, is it visible or is it not visible, as opposed to like how much can we see it? And then we define our thresholds in terms of temporal frequency. So at a given spatial frequency and eccentricity, what is the maximal perceivable temporal modulation, or the eccentricity dependent spatial temporal flicker fusion threshold? So this vastly reduced the number of samples that we need to characterize this space. Additionally, we further reduce the number of samples in spatial frequency and eccentricity by recognizing the effect of the uncertainty principle. So that is, low spatial frequencies cannot be well localized. In space, so like a 0 cycles per degree stimulus is constant across the entire retina, whereas if you've got a high spatial frequency, you can localize it in space. So we use this idea to optimize our sampling strategy, choosing 18 unique wavelets. So this is based on wavelet theory, to keep the study duration to under 90 minutes. So it's still a 90-minute study just to measure all of these sensitivities once. And that includes 6 spatial frequencies where the size of the Gabor, so this wavelet pattern, is scaled with frequency, such that each captures the same section of the sinusoid. So I've got a question from Jim here. Does the lateral geniculate nucleus and blind sight play a role in any of this? I'm not sure what the geniculate nucleus is. Are you, is it possible you mean the blind spot? I'm not entirely sure what you mean. I don't know if you can unmute because it's a webinar, but maybe you can.
Right here.
Sorry, what was that?
He should be able to unmute himself now.
Oh, okay, cool.
Yes, can you hear me?
Yes, thank you, Jim.
Yes, for example, if someone is blind due to a problem of the primary visual cortex, you can throw like a tennis ball at them and they will catch it. And it's because there's vision that occurs in the lateral geniculate nucleus portion of the brain. And it's a low level type of vision. You better study this for your defense. It's sort of a low level type of vision that is good at for orienting towards danger and things like that. But it's something that occurs outside the normal pathways of the visual system.
I wonder, like, I spent a lot of time searching for a reason why we have a higher temporal sensitivity in the periphery, and particularly it comes down to like reaction time, like that, like the activation sort of like ramp up is much quicker in that sort of section. And there were a couple of different competing theories, but no real consensus. It came down to like the speed of the axons or something was the going theory, but like I never really came to a good conclusion. So I wonder if there's any kind of relation there, like parts of the brain would be connected.
Yeah, there may be an influence.
Super interesting. Yeah, I spent like way too long trying to find an answer to that because I just wanted to know, even though it wasn't really important for the project. It was just like, I want to explain this to someone, like intuitively why. I think everyone knows why, or at least it's well understood why, like our spatial sensitivity is the best in the fovea, because like inherently the connections between the photoreceptors and the ganglion cells are one-to-one there, and it's all fine. But temporal, people are like, oh.
Yeah, I think it seems to be something to do with orienting and you know, perhaps reaction to emergencies. The fact that a blind person can literally catch a ball that you throw to them using just that sense tells you that it has a lot of capability.
That's super cool. Super cool. Yeah, I think it's like a hazard of doing research, though, is that you now start to look for these phenomena in the world. Like I think my partner hates when I'm like, oh, look, street light flickering. Look, you look at it, you can't see it. So I feel like that's gonna make me, I don't know how I would throw a tennis ball to a blind person, but I want to try it.
All right.
Thank you for that, Jim.
Okay.
All righty, moving on. Okay, so then we built a custom monochromatic VR display capable of displaying up to 360 hertz and up to 60 degrees in eccentricity. And we temporally modulate such that at high frequencies, the stimulus would kind of appear to fade into the background. And then we run a user study and we find a threshold for each wavelet by finding the temporal frequency at which a subject could no longer distinguish flicker when forced to choose. So essentially in the middle of COVID in my backyard in Australia, because this is what happened, got an IRB approved and had a lot of people look through this VR headset and tell me which side of the display they thought was flickering. Until they had to guess is essentially how we do that. There we go. So then we average all the users and we end up with some data that looks like this. And then we can do some fancy hand wavy math and fit an analytical model to those data points, which we can use to continuously predict these thresholds for an arbitrary spatial frequency, eccentricity, and even fit an extension for varying luminance. Where am I? Yes. Now that we have a nice model, we can see some important trends. Okay. Of course, spatial acuity drops with eccentricity. So this is spatial frequency and the threshold. So if you look right here, let's do that. So it drops with eccentricity. So as you go up in eccentricity, so the yellow is the higher eccentricity. So we're going this way. We can no longer detect these higher spatial frequencies. So that makes sense. And even more so, like some of our users just couldn't even see the actual patch because their acuity, so just their ability to see spatial detail was too bad out there, which makes sense. Also agreeing with pre-existing literature, lower spatial frequency. Okay, so lower spatial frequency, these big patches up the top here, and higher area gives a higher temporal sensitivity. That makes sense. If you flicker the whole display, you're more likely to see it than if you flicker only a tiny little patch of it. And that's similarly related to spatial frequency. This is known as the Granite-Harper law, if you're familiar, and other papers have shown this as well. But perhaps what is least well known is the increase we can observe from the fovea towards the peak, between about 10 and 30 degrees eccentricity. So again, confirming this anti-foveated effect. Like we could, in fact, like some of the users could lost detection, in the fovea at 60, but could see up to 70 hertz, for example, in the periphery, and more as you go higher. So there's some really interesting trends here. Again, this like anti-foveated effect. Okay, then to validate our model fit, we conducted another user study, which we showed users videos. So here's an example of a frame in that video in which some of the areas were perturbed with carefully chosen spatial-temporal frequencies. So similar to the Gabor wavelets that we used in the first study, but it's kind of hard to show you exactly what they look like because this is not going to be the frame rate high enough to really visualize it. But you can imagine this little patch is kind of modulated in time. So it just looks like part of the image is like just flickering. You have to trust me on that one. And then we asked the users to rate the quality of the short videos. So some ratings, bad, poor, fair, good, excellent, all the usuals. So we showed that when we chose signals that our model predicted were perceivable, even if they're as tiny as just this one here, then the users consistently rated the video poorly. Makes sense, it was flickering. But on the contrary, we could perturb almost the entire field of view with a variety of signals. So these are variations in time, but because we chose these because our model predicted it would be imperceivable, the users would still rate the videos as excellent. Like we were right, they are not perceivable. Furthermore, these user ratings could not be predicted by several video quality metrics, including PSNR, SSIM, and VMAF, which is a video metric used or developed by Netflix. So this suggests that with our model, existing foveated compression schemes may be able to utilize more degrees of freedom to achieve higher compression gains. Cool. And finally, we conducted a little thought experiment where any signal outside of the visible gamut is removed to estimate an upper bound on the bandwidth savings in computation or data transmission that could be achievable given the characteristics of the visual system that we just measured. So while such an estimate will depend heavily on the total number of pixels, we can kind of parameterize this in terms of pixel size and field of view and generate plots like this one. So if you look at the 1 arc minute pixel size, this would be like a retinal resolution display. This is at our visual acuity limit. Unsurprisingly, we get significantly more gains when you add our like temporal foveation approach. So at like a refresh rate of about 200 hertz, we can see that spatial only foveation here achieves about 500 times savings at a field of view of 120 degrees. However, we could add an extra 7 times savings there if you could also temporally foveate. So there's still untapped potential essentially in these techniques to reduce bandwidth. We don't present in this work a way to do that temporal foveation. We just show present the first model to say, okay, how high do we need to go? Like, what is the frame rate that we need across every single position in field of view, depending on what content you show, what luminance you show. All right, I have a question here from Kenji. Were you looking at mainly 2020 normal foveated subjects, or do you have people with larger normal visual acuity or larger than normal foveas? We tested everyone. So like the inclusion criteria was 2020 vision up to, but could be corrected to normal vision. So there were some people with contacts and glasses, but had to be able to pass a 2020 test. I would love to learn, like, if you're comfortable going on video, I would love to learn what makes you ask that in the context of this, because I would always love to make it better. Yeah.
I'm actually looking more in the direction of people that have, like, 12, 20, right, vision, or have super large foveas, people like pilots, or people that have higher than normal resolution of visual acuity, mainly because some of the stuff I've worked on, these standards are great for people with 20/20, but anyone who has better than normal vision like myself, sometimes these techniques still leave a lot to be desired. So I was just curious if you looked at people with higher than normal quality. Thanks.
Yeah, definitely. The answer is that there was definitely variation from within our subjects. We haven't like directly studied more that like this kind of population, just due to getting some model is like a good start to have than nothing. I did notice, interestingly, and perhaps you noticed this yourself, it's like, for myself, who did the user study, I don't even know, hundreds and hundreds of times before like actually deploying it out to everyone else. There was a definite training effect. So you can definitely train yourself to see the flickering more than the average user. And I wonder how that might be taken into account for exactly like the pilot example. I wonder if, in your experience, are you able to is a scale factor enough to deal with that, or have you found that it's widely variable between that population?
It gets complex pretty quickly when you're looking at communities like fighter pilots that have much higher visual acuity than the average person. The other problem is that a lot of times VR equipment, things like that, has been traditionally used to train those kind of people. And so you have negative training effects because you have a display that's calibrated for 20/20, which for that population still looks terrible, right? So it gets very interesting in that area. We can't even hit 20/20 right now necessarily. So, I was just curious if you looked at that.
Yeah, I was going to say,
and you can definitely see training effects.
Yeah, I see it with myself all the time. It's kind of fascinating. At the very end, you've almost predicted where I'm going with this, but the very end, I wanted to give I'll give a high level about where I think this field is going. And one of the number one concerns is going to be how do we do per user calibration? Because you're right, there are such variations that these generic models aren't enough.
Thank you. Yeah, I was just curious.
Yeah, cool. Thank you for the question. From Jim, is it possible to derive off-axis sensitivity to spatial frequencies from the Nyquist sampling theory and the density of photoreceptors in the eye in those areas? The answer is yes, you can kind of create an upper bound, but it's not quite as simple as going by a Nyquist sampling theorem and density of photoreceptors. You can definitely get much worse visual acuity based on the scattering in the eye, the optical distortions in the eye, and various other lens effects that make a lot of people's visual acuity lower. And the effects of putting vision correction and things on. But actually there's some weird effects also where people have higher visual acuity than that theorem would predict. And there's a couple of theories there. So while that is a good average, I would say, or a good like ballpark number. It's not perfect. And that is honestly some of the hardest bits of this research, is that like just the variation between people that you get, and just the body does some weird things and cool things, and trying to account for all of them means that we result back to these psychophysical studies. So these like actually put a person in front of a display and tell me what you can see. Perhaps a lot, maybe perhaps more than I would like. It just takes a long time to run them, even though you get some interesting results. Liana Yee is going to answer this question live. I don't know if that's right. I'll just keep going and interrupt me if I've misinterpreted. Okay, so jumping on from this, I have a little teaser for you guys. So we can also jump off this idea that there is untapped potential in foveated rendering, and make the observation that these techniques have typically focused on matching the capabilities of the visual system under the best of circumstances. So these are controlled experiments where the user is focused on the visual task at hand and sort of nothing else. So for example, in the previous study where we asked the user to kind of focus blankly in the center and observe this, so their eyes are in the center, but they're really focused on what's happening in their periphery, observing what's going on, which is a pretty unnatural state to be in, really, in the real world or VR and AR. So as these displays become more ubiquitous, and increasingly designed for long-term use, where we may be less focused on the visual quality, say when concentrating on smashing your boyfriend in Beat Saber, one could wonder, does this affect our spatial-temporal perception? Would I notice if the rendering quality in the periphery was slightly degraded if I'm focused on smashing these Beat Saber blocks, for example? After all, perception is a combination of vision, that is the signal that is collected, but also the cognition, so how our brain processes or makes sense of that information. So stay tuned for work in SIGGRAPH this year on that. And moving on. So the second thing I want to talk about, project I want to talk about, is the emergence of wearable eye tracking in VR and AR systems also enables the rendering of dynamic gaze effects. So these include focus cues. So for example, that blur that you get, if you can look at your finger, you notice that the rest of the surrounds kind of looks blurred. That's a depth cue, actually. Similarly, pupil steering. So some of these new displays have such small eye boxes that you want to be able to sort of move the display around as the eye rotates. And for that, you need gaze information. It's a type of gaze-contingent display. And similarly, the distortion correction. Often it's thrown around the word pupil swim. Essentially what this means is that the lenses are centered on your eye when you're looking straight ahead. But if you rotate your eye left and right, suddenly the barrel distortion of that element is not centered, and it creates this like warping effect. Again, if we know where your eyes are or how they're rotating, so using a gaze contingent display, we can actually apply distortion correction to improve that. Now I want to discuss how it can also improve depth perception via stereo rendering. But first, let's quickly review how stereo rendering is done today, and which is pretty much how it's been done since the 1800s with the first stereoscopes. It hasn't changed that much, which is kind of surprising. So today, most conventional AR and VR systems consist of some kind of near-eye displays for the left and right eyes. Now, these are magnified by a lens or by lenses to create a virtual image at some distance, often, 1 to 2 meters away, like so. Now, say I wanted to make this pixel appear at some distance closer than that. Then conventional disparity rendering uses the geometry of the system including the user's IPD or interpupillary distance, that is the distance between your eyes, in the form of matrices, to essentially trace a line between that position and the centers of each eye. The points in which these rays intersect the screens tells us the pixel coordinates to light up on each display, so these ones here, such that the light lands on the retina and gives us the perception of a point at that depth. This is through a process called stereopsis. However, part of this approach is physiologically inaccurate, specifically the use of the center points of the eyes. So we actually showed that the optical center of our eye is also known as the no parallax point, if you're familiar with camera terminology, or the center of perspective, is actually slightly forward offset from the center of rotation. So around 7.29 millimeters. In fact, we measured it with a user study. That's me in the user study. It was a fun one. Cool. So when a user verges far, so they're looking at a far distance, this finding has no effect, as the distance between the pupils, the IPD, is also the distance between these no parallax points, because they're parallel. All right. But if you look to an object that's close to you, so you verge closer, those points shift inwards. And if you could see the animation there, the IPD actually shrinks, which means that this measurement is actually gaze contingent. So it depends on where you're looking. So this means that the geometry of this disparity calculation depends on where you're looking. So the rendering depends, like which pixels that you light up on the screens depends on where you're looking in the scene. Now, it's a seemingly small shift, but we actually showed that failing to account for it can lead to significant errors in this depth calculation. That has the effect of distorting the depth space at those distances closer to you, and leads to objects actually appearing closer than intended by the rendering, which is why we developed Gaze-Contingent stereo rendering, it was published in SIGGRAPH Asia 2020. Okay. So with access to gaze position, it's possible with increasing use of inbuilt eye trackers. We can modify the matrices used in this stereo rendering to trace out the center of perspective to be at this front no parallax point position, and then proceed as before. Now, to show that conventional stereo rendering is in fact inaccurately rendering depth, and that we can address this with this approach, we conducted, you guessed it, more user experiments. So in the first of which we used a Vive Pro VR headset to show an effect on shape distortion. Okay, so bear with me for a second here. This is based on the hypothesis that if the depth rendering is in fact being distorted by this conventional stereo rendering approach, this will distort the 3D aspect of a shape. So for example, in a cube, if it's being distorted, you can imagine it being stretched, that depth space being stretched. So a cube, even though it was tried to be rendered as a cube, you're perceiving it to be like longer than it is, because that depth space is being distorted. To ensure accurate shape construction, we used what's called a random dot stereogram stimulus. This looks like a pair of random dots, but when you view this with a stereo display, so you show the images separately to each eye, it's kind of amazing. If you view them in anaglyph, you can see that some of the dots have been shifted left and right, and this by a calculated amount, and this actually produces the sense of a specific depth. So in this case, it would be like a ring that feels like it's popping out of the display level. And we can make these calculations to shift these dots to create any kind of shape and depth that you want. So we use such a pattern. I don't have any anaglyph glasses to hand out, but you can kind of see it, if you will, there. So we use this pattern to render a triangle wave. But since it kind of looks like the accordion folds that you can make in a piece of paper, but like jutting out at you. And what we did was essentially calculated it so that the amplitude and depth, so this is amplitude and depth here, is half of the lateral I don't know, length of it. So essentially what you're constructing is 90-degree angles here facing the user. Now, if our hypothesis is correct and the way that we typically render in stereo is inaccurate, then these peaks will actually appear more pointy. So they'll be smaller than 90 degrees. So sure enough, we showed a user a heap of these patterns and asked them, which did you think, which of the two sort of between conventional and our approach was closer to 90-degree angles? And sure enough, at 0.3 meters and 0.5 meters, they thought ours was much better. Will the angle remain constant? From JMeet. It's like you're trying to render it. So like when you type in the parameters and you do the calculation, you're trying to render it so it's 90 degrees, but because of the depth calculation going on, you perceive it to be less than 90 degrees because that inherent like rendering calculation is wrong. Whereas ours should be closer to 90 degrees because that inherent like calculation of doing the fusion of images is more accurate. It's kind of hard to explain. Now perhaps this one's easy to get. The second user experiment investigated the effect of accurate depth rendering on the alignment of real and virtual objects in AR. So this is an application where a tiny inaccuracy could mean life or death. I mean, I don't know about you, but I would, if a surgeon's going to use this to decide where to cut into me, I would hope that it's aligned with like millimeter precision accuracy. Particularly, again, this application is where it's going to be used where the stimulus is quite close to the face. So again, that divergence angle is the tight one. So this is where this effect really occurs. Here is an example of the user experiment that we did. So you can see there's a physical target. This is literally a piece of paper mounted to like one of those optical stands. And we placed this so you can see the tape measure measured at exactly 2 meters away from this user's eyes. And then we rendered the stimulus and we said, according to the rendering calculations, render it 2 meters away. And then the user was asked to compare which of the two conditions, so whether it's our rendering or conventional rendering, is more accurately aligned in depth. So between those, the real and the rendered. And we showed that for a distance of 0.5 and 1 meter away, that ours was significantly better aligned. So we bring those two, the depth alignment better, more accurate from the real and versus virtual. Now, I will put like a bit of an asterisk here because you're like, why hasn't this been done before? Like, surely like this has been noticed before. And the reason that it hasn't been so important to date, we've done stereo rendering the same for 100 years or so, is that we're now only just getting displays that can deal with the divergence accommodation conflict. So right now, if you put on, which was why some of this was a little bit challenging, if you put on a HoloLens, a Microsoft HoloLens device, and you try and render up close to your face, it will look blurry. And the reason is because that virtual image that gets created from the lenses and the display is a meter away. So you are focused on that display a meter away, but you're trying to like verge, your eye rotation is trying to focus, however close that you've rendered it. And so now with some of these new varifocal and multifocal and all of these new displays that are coming out now, we're now getting displays that can deal with sharp content up close to your face. So this is going to become more and more important, particularly since surgery and industry and other of these applications are begging for these devices. Cool. So taking a step back, what I'd love for you to take away from this talk is that VR and AR are only still really providing immersive experiences. We have a bit of work to do to really create perceptually realistic ones. And for that, we need to have an excellent understanding of our visual systems. So today I talked about 2 projects that work towards this goal, one of which is the modeling that visible gamut, the spatial-temporal, what is visible in the spectrum of things across our visual field, and the other one looking at improving depth rendering by knowing sort of how our eyes, where we're looking in depth, our eyes are rotating. And while each of them have their own future work, you can read all about this in the papers if you're really interested, or email me, ask me later. Instead, I'd like to quickly zoom out a little bit and talk a bit more about the goal of attaining perceptual realism and passing this visual Turing test, and as sort of a broader topic. So where do I think that we need to go from here? What are the big challenges that face this field? For one, eye tracking. I don't know, for some reason, people think that eye tracking is kind of a solved problem, like it's a technology. At least that's my experience. And from my experience with working with it, it is not. It's kind of funny that the very technology that enables all of these cool display techniques is really the biggest thing holding it back. It's certainly come a long way, but even in terms of accuracy, but more than that, like the power consumption and heat dissipation and per user calibration is really, really challenging still. It's a big sort of point of contention where I'm talking about like, hey, we're saving bandwidth and power and transmission and all that with some of these techniques, when they hinge on having eye trackers on board, which inherently have their own power consumption and bandwidth requirements. So we've made some progress there, but there's definitely more work to do. And there's a couple of cool startups that I think are making really good progress there. The second is accounting for individual differences between users. I can see there are 2 questions. I'm going to finish off and then I'll jump back to the questions. Accounting for individual differences between users. So for example, like we talked about a particular user's spatial-temporal sensitivity function, it really does vary person to person. And like, how are we going to quickly get, how can when someone buys a headset, can they do a couple of quick points for us to be able to calibrate that function? Similarly with this, like no parallax point in the eye, that 7.29 millimeters that I threw around there is an average. We averaged it in our user study from the people that we tested, but it is different in every single person. So how can we do a quick calibration to be able to make sure that this depth rendering is really accurate on a, not just better than conventional, is accurate for every single user. Furthermore, it's going to be one of the, it's simple, but it's a really hard problem, is that each of these techniques needs to be adjusted and integrated with a user's individual prescription corrective optics. And prescriptions vary, and it does some strange things to some of these techniques. You've got just, extra distortions in the periphery. You've got, you can imagine that the position of the lens will shift that nodal point, that no parallax point. How do you deal with that in the rendering? It's like, I don't know, it's simple, but I know that some of the big companies are still struggling with this. And finally, we've got lots of people, including myself, publishing papers on different gaze-contingent display techniques, but it's still a very big question about how do we combine some of these together to get all the benefits of each of them individually. It's not trivial. like in a perceptually correct manner, like can I combine this spatial temporal rendering with this gaze-contingent display? Like, is there going to be any kind of crosstalk essentially between the two? And I think that's a big question mark, and perhaps something that the research community in particular isn't super motivated to work on, you know, given like publications and things as a motivator. Anyway, I have talked your ears off for many too long. So with that, I would love to answer some questions. Thank you. So I think I'll just dive into it if it's okay with you, Alish. Okay, I'll just dive in. So I'll start with Ken. I think I saw first. Queued up the question. With foveated rendering, is it better to have the periphery with big square pixels or blurry pixels? Maybe you answered it. Aliasing of the square pixels will flicker in the periphery. Yeah, that's a hard one. And also, so I'll just jump into that one. It's kind of a bit of both, like a fusion of both, which is hard for the computer graphics side of things. Because if you just straight blur the periphery, particularly if you're looking at, let's say, a stimulus with, like, I don't know, like imagine a city scene where you've got lots of skyscrapers, for example, the vertical edges, like your periphery is actually sensitive to like to edges in some way. So if you completely blur them, it'll create a sense of like almost motion sick, like nausea, like it'll look funny and you won't really know why. So a few people have experimented with a couple of different, like applying different spatial filters, and that seems to be the best way to do it, like what are they called? Bilateral filters, I'm remembering that correctly. And that seems to be the best of both. The tricky bit is how you do that in a way that's computationally efficient, so you're actually getting the benefit of both saving computation as well as transmission of pixels. If you're interested, some of the work in foveated compression in particular has been particularly cool. Just like straight down sampling is pretty good overall. And then 2, is spatial and temporal sensitivity isotropic, or is it greater in the horizontal or vertical directions? It is not quite isotropic. From memory, it's slightly better in the horizontal than the vertical. But in the grand scheme of like compared to like variations between users and things, it's probably negligible. In that particular study, we just modeled it in one direction. So we went out to the temporal side and kind of made the assumption that it is rotationally symmetric. There are a couple previous papers that show that there are minute differences, but like probably in the grand scheme of things, it makes more sense to just go for the maximal case, and which is the temporal, and that's good enough. Lots of questions. From Tom, do animals, dogs, say, have similar characteristics? Oh, I was reading about this recently. From memory, it's somewhat similar, but I'm not a super expert, so I don't really want to comment. But they have done some studies, particularly on like monkeys. But it would be interesting to know. You would think, I mean, based on my dog's behavior, he's got higher temporal sensitivity in his periphery. But I have to get back to you. Is there work done in SIGGRAPH for IPOs? Do you think research is needed in this area? For IPOs, yeah, I don't, my gut is no. And the reason is because yeah, that's a good question. The eye, actually in VR and AR applications, the eye doesn't move a heap. Like like actually, if you look at the statistics of the eye, you could probably simplify the dimensions down, because most of the eye movements actually happens in the axes. Like I think it's something like if you put up someone in a VR headset and then you tell them to look around the scene, like 80 to 90% of eye movements will be in these two directions. So you could, my gut would be you probably wouldn't need it of all the different problems in VR, but that's just my gut. What do you think are the main reasons for fatigue with these headsets? There's a lot. The main ones. I want to like, I'm no expert in this because again, I'm more looking at like specific use cases, but from my experience using it, I want to say that like when you're in VR, a lot of the times, like you're constantly doing something, like you're not in a restive state, like you are just as a user sort of looking out into the world. So it definitely amplifies that way more, I would say. I don't really have a good intuition for that one though. It sounds like the next speaker though, Will. Apologies, I haven't got a good answer for that one. Did you find any connections or correlations in your studies with subjects who had color vision deficiency? Oh, I wanted to look at color vision deficiency, but we tried to keep it, well, we had to keep it to normal viewers, at least for this generic model. So we excluded anyone. We tested everyone for vision deficiency and excluded them from the study, but it would be a super interesting access to look at. And I think I've got some colleagues, some collaborators over at NYU who have looked at this as well, and actually looked at the degradation in color sensitivity, even for normal viewers in the periphery, and using that to save. So you can degrade the colors and save bandwidth and power and other things. And there's some really interesting work there. So if you're interested more in that, I'd go and look up that work out of Chi-Sun's lab in NYU. Super interesting paper. I think it was published in SIGGRAPH Asia last year. But no, we just did a generic model. And Greg, has there been much study of AR registrations issues in real world scenery and problems, distortions, and nausea with those? Yes, there has been a lot of studies. Same with depth estimations and things. Like we've been shown to definitely underestimate far distances and overestimate close distances. And yeah, lots of study of that. People still don't know why, like we address some of it, but still not the full scale of why that perspective shift occurs. I don't know about nausea in AR.
Can you hear me?
Yeah.
Yeah, I was also interested in synchronization issues, you know, where you're trying to track things and keep them in place.
Yeah,
any studies on that?
Yeah, huge. And same with like, I mean, it's essentially world lock rendering for AR, right? The ability to keep it steady. I mean, something that I haven't really talked about, but latency is huge in some of these devices, especially like we're now seeing these eye trackings start getting into commercial devices, you know, the Vive Pro Eye and things like that. And, you know, they report update rate, right? Like 120 hertz or 90 hertz or whatever it is, but that is the throughput, not the latency. And latency is just challenging overall. But hopefully if we can, like the idea of reducing bandwidth and transmission should hopefully reduce that latency. But yeah, there are heaps of studies. If you're interested in anything in particular, happy to comment on what I know.
Thanks.
No worries. Okay. Q. Oh no, that's just a comment. Thank you. Thanks for attending. Appreciate it. And think our motor skills may not. So Jamie T said, I think our motor skills may not be quite calibrated with physics used in VR space, and maybe that's why we feel mentally fatigued. Yeah, that is a very good point. Also, the like kind of to the other point, latency as well. Like that persistence of vision is a big one that could contribute to that. But there's just so many factors. It's very hard to isolate all of them. For one, like I briefly looked into motion sickness, and it's crazy how not well that's understood as well. Like there are several theories, but no one's really been able to conclusively confirm anything. Cool. Is there any other questions? Thank you for all this has been great questions. Thank you for listening in. I've appreciated the audience.
I think Jim F asked one more question.
Oh, can I not scroll? Did I miss one? She just said about the motor skills, right?
It's in the questions.
Yeah,
okay. My bad.
Do visual saccades pose a challenge for foveated rendering?
They do, but we do have a little bit of, like, the nice thing about visual saccades is that we have saccadic suppression. So that gives a little bit of tolerance. So for anyone that's not aware, when you're about to saccade, while you're saccading, and after you've saccaded by about sort of 50 milliseconds each side, you have a gap in perception. So you can imagine, I mean, you can understand why that is, right? If you're going to like swing your eyes across the room, you don't want that perspective mood like getting picked up in your cognition. So it kind of just suppresses that signal. So that can definitely reduce the latency requirement. I would say that, yeah, while it's a challenge, the biggest challenge is still the like inherent accuracy and latency of the eye tracking and the update rate. We're far from, like, that's far from the biggest of problems in foveated rendering right now. Also, look at the frequency of saccades; they're pretty low overall. So it'd be like, if you like for the big ones, that would be really effective. It's not too bad. We tend to move our heads here.
Yeah,
sorry.
great. Thanks a lot.
No, thank you. Any improvement on focus if someone do eye exercises? Interesting. When you say focus, you mean, what do you mean by focus? It doesn't have a few meanings. If you are okay to unmute or just comment on it or something. Like focus in VR, like focusing of the eyes. Oh, like as in like on a task at hand. I don't know about eye exercises. I could imagine, like, I think definitely you can train yourself to use it for longer periods. Like the first time you use a VR headset, you might get very fatigued and you're like, I have to take it off, like my eyes hurt. But the more and more you use it, you become more accustomed to it. And they've found that people can do it, like stay in them for longer the more that they like do it. So it's kind of like eye exercises, if you will. I don't know about specific. I love that from Jim. As we get older, focusing ability goes down the tubes. That's good. Yeah. It's also when you're younger, there's so many distractions around these days.
One more question.
Did you find any gender differences in visual acuity or noticing frequency aberrations? I didn't, not in the sample size that I had, though I was, interestingly enough, I was able to find like Okay, that's a lie. I did find a slight difference where males were better, but I don't know if that was biased because the guys that were kind of skewing my data set upwards were all video gamers. So I have a theory that it was because they played video games, they're used to monitoring the periphery for, whatever, like rifle shooter or whatever was gonna kind of come out, and they did better. So I don't know if it was actually gender or that was playing a part, but I did find that really interesting. My maximum field of view was 60 degrees. It was slightly, it was higher than that, but we just used, I think like the total field of view was 80 degrees, but we used the center 60, and you get the user to focus on one side and then you show it on the stimulus on the other. The reason was that we did that was because we cropped the edges because the lens distortion was just too bad. It was a nice way to at least theoretically test it, what it would look like for a 120-degree display.
Okay, if there's no more questions, perhaps we can wrap up this meeting then. And you just call one more time. Any additional last-minute questions? Okay, it looks like, thank you very much, Brooke, for coming to our meeting. We really enjoyed having you here, and it was a great talk. So I wish we could applause, but there's no Alexander's way of doing down Zoom. So thank you very much.
Thank you.
Okay.
Have a good night, everyone.
Thank you, Brooke.
Thank you.
Okay, and that is all bring the meeting to an end. Okay. I'll see you all in the next one then.